Okay, folks, so we need to go back to some actual learning today after all of our tests and everything. So we're going back to halogenoalkanes. You should all have, hopefully, your wonderful knowledge from doing CPAC 4 on hydrolysis of halogenoalkanes, okay? In particular, which ones are hydrolyzed quicker than others in that particular reaction, okay? What did we find out? Which halogenoalkanes are hydrolyzed the fastest? Leanne?
Iodobutane, I believe, from the ones that we talked about, iodobutane.
Okay, so from what we talked about, the iodine attached halogenoalkanes were quicker, yeah? So the order went iodine back up to bromine and then up to chloro, which was the slowest, yeah? What before, I know you're going to answer something about primary, secondary and tertiary probably, but before we go on to that, what was the actual reason behind that? Okay, because there's two possible reasons, isn't there? There's the polarity of the bond, or there's something else. What was the reason behind iodo being hydrolyzed the fastest? Good, Jemima, go.
It has the weakest bond strength.
Okay, it has the weakest bond strength. So it's got the smallest bond enthalpy. So it's got the weakest bond. Okay. So it's not about the polarity of the bond, it's just about the bond strength itself. Okay? Did anyone find out in their research why the iodo bond was weaker than a chloro bond?
I think it's to do with ionic radii. So I think because it had a lot more electrons than it was, the distance between them was bigger, so that meant the electrostatic forces of attraction were weaker.
Okay, you're pretty much right there. The only thing that I would pick you up on, rather than ionic radii, it's about atomic radii. Okay, so basically with an iodo bond, a carbon to iodine bond will be longer than a carbon to chlorine bond, and the longer the bond, the less strong it can be. Okay, and it's because iodine has got so many more electrons than chlorine and bromine have. Yeah, excellent. Okay. And then you also did primary, secondary and tertiary. I think we kind of maybe mucked up the tertiary one a little bit in our experiments. Or a few groups kind of didn't get around to quite doing it. But what did we actually find out? Which is hydrolyzed the quickest, primary, secondary or tertiary? Someone apart from Jemima and Leanne would be good at this point to share ideas with me. Bisma? Tertiary. Okay, good. So tertiary was hydrolyzed quicker than secondary or primary. And again, I'd ask the question, why? And everyone goes quiet. James?
More stable because the positive I think I read something about the charge doing strength across more carbons.
Okay, so when we come, and this is going to come on to today's lesson, we need to look at the mechanism for this reaction. Okay? It's going to have an ion in the mechanism, and so the ion for a tertiary is more stable than the ion for a secondary or a primary, yeah, which is actually what we found out when we were doing alkenes and electrophilic addition as well, wasn't it? The carbocation, the tertiary is more stable than a secondary, and a secondary is more stable than a primary, yeah, and that's the reason for the difference in those hydrolyses. Yeah, so there's a massive recap on everything that we've just done, but today is all about looking at a reaction mechanism, being able to draw another reaction mechanism. We'll be up to 3 by the end of this. We've done free radical substitution, electrophilic addition, and today's one, we're about to find out what it is. Okay, so let's have actually a title and let's make sure we've got some notes for today. Oh, I can't fit it all on. Reactions of halogenoalkanes. So, time to get rid of that pen as well. Yes. I don't actually have any new books at the moment. Can we... Do you reckon you can go down and ask for some new science books, green science books for me? Yeah? Thanks, Janavi. Cool. Okay, so reactions of halogenoalkanes. We've looked at already hydrolysis. So I'm just going to sort of list out about 4 reactions that we need to know, okay, and then we'll go back and we'll look at the mechanism for 2 of them, okay. I'll help you with 1, and then hopefully you're going to use your knowledge to do the second mechanism, okay. It won't be very much different from the first. So, what halogenoalkane will I pick? That means you've got to help me. You've got to come up with a halogenoalkane. Doesn't matter which one particularly, as long as it's not too complex. Leanne? Bromobutane. Okay, let's do bromobutane. Let's go. C. Here we go. Now, this is exactly what we made happen in our practical. What was the other condition that we needed just to make it reasonable speed? Huh? No catalyst. A little bit of heat. We had to warm it up, didn't we? Remember, we had to put all of our reactants in a water bath, so we warm it up. Okay. What did it produce? What was the actual products from that? Exactly. It's it's an alcohol, C4H9OH plus, what's the other product in that case? HBr. That's the only thing that's left. Okay, so if this is 1 bromobutane, then what is our product here? We've gone terribly quiet about that. Go on, Ziad. It is butanol, but we need a number. Butan-1-ol. I think you're all going quiet because you're a bit confused where the number goes. Whether it should be like but-1-ol, and which is not quite right. It needs to be butan-1-ol. So butan-1-ol. Okay. So that's one hydrolysis reaction. It's okay like that, but it's much better, works much better if I use OH minus ions instead. Thank you, Genevieve, for getting those. Okay, so if we're using hydroxide ions, what kind of substance are we actually talking about? Oh, the quiet. We're having a quiet day. If we're using OH minus ions, what kind of substance are we talking about? Huh?
An alcohol?
Not quite an alcohol, no. Would it be? Not that, definitely not that, Pranesh. No. What I mean is, like, if we add OH minus ions, what kind of a substance am I adding? It's a... Yeah, no, it's a hydroxide, I just said that. It's an alkali. It's an alkali. Okay, we add potassium hydroxide or sodium hydroxide, we're adding an alkali to it, okay? It's not just water. Maybe that was me asking the question in a bit of a silly way, I don't know. So, what will our product be though? Will it be any different from this? Do you think? We've got some nodding, we've got some shaking. Nobody wants to commit. James?
I think it'll produce it'll produce butan-1-ol, but it'll produce an acid with it.
Almost. It will produce butan-1-ol. C4H9OH. Butan-1-ol again. what's left over? Br minus, yeah? Huh? I'm not sure that there is a hydrogen left. If you think about this, then, okay, the OH minus has substituted for this, okay, and this goes off with a negative charge. To do this with an alkali is much the preferred route rather than just using water, okay. Most of the time in exam questions you'll be answering with, you know, how do we hydrolyze a halogenoalkane? With OH minus, okay, or with potassium hydroxide, something like that, okay. So, 2 hydrolysis reactions. This is a really interesting reaction next. It's really important as we start to think about how we can make certain chemicals. This becomes important. Okay, we can extend the carbon chain with a halogenoalkane. So let's start with our 1-bromobutane again, C4H9Br plus this stuff, KCN. Have you ever seen that before, CN? Probably not, to be fair. Okay, go on, Ahmed, you may have seen it before, you just said the word, I think.
Potassium cyanide.
It is, it's potassium cyanide. Has anyone heard of cyanide before? In what context? It is exceptionally poisonous, absolutely. Okay? Yeah, used for all types of nasty things over the years, okay? I won't go into it right now, probably not appropriate. Potassium cyanide is kind of, it's kind of okay to use. I'm not going to let you use it in the lab, by the way, just in case anyone kills himself. Don't want to be responsible for that particularly, okay? But it's hydrogen cyanide, the gas that can be produced by that is exceptionally dangerous, okay? So yeah, you're not going to get to use this in a lab. Sorry about that. But this makes fairly interesting looking product. Okay, again, it's just going to substitute out the bromine for the CN. So we end up with C4H9CN. Notice now how it's got an extra carbon atom in the chain. Okay, and all that's left over, well, what is left over? The Br and the K. So KBr. Okay. This kind of compound is called a nitrile. In this case, this would be called pentane nitrile.
Sorry.
Yeah.
Isn't a nitrile like I think I'm getting confused with nitrogen, the nitrogen ion, like I'll have to explain that.
Nitrile.
It's called a nitrile, yeah, exactly.
Okay.
Yeah, but yeah, I'm not sure where the confusion might be. There are other things that have that sort of beginning, like nitrate and so on, but a nitrile is specifically this carbon, and it's just joined to a nitrogen. Okay, if you were to look at the bonds for that, I could just, yeah, actually C4H9. Actually a triple bond from the carbon to the nitrogen, and then the other bond is on this side, okay? That's specifically that nitrile group, yeah? And somehow we've gone now from a butane to a pentane. Great reaction for extending the chain and starting to make and design your own molecules. Yeah, that's where we will get to with organic chemistry, is basically designing our own molecules to make a certain thing. Okay, it's really cool. That's why I love organic chemistry. So there's 1, 2, 3 reactions. There's only one more. Let's have a little look at, and then we'll do some work on mechanisms. So extending the carbon chain to make a nitrile. The other one, can I fit it on somewhere? Yeah. We're going to do the reaction with ammonia. Okay. Actually, before I go on to that, I've just missed out something really important. To make this happen, I'm not sure I've talked about this process much before. We will have to do it in our next core practical. We call it heat under reflux. Have we mentioned that word before, reflux? Mr. Collins has. Do you know what it actually means? Okay. It's a really, really important practical method for organic chemistry in particular, heating under reflux. It's a bit like distillation, but rather than having a condenser off the side, we have a condenser coming vertically out of whatever we're heating up. And that means we can heat a mixture, it can evaporate, it will go up a bit, condense, and come back down. And we can keep heating a mixture of quite a volatile compound. It will boil, condense, come back down again, and we can keep heating it. Yeah?
What happens? Like, it's a cycle, it keeps going, but then what's the actual ending of the product?
The aim of it is so that you can keep heating it so the reaction will happen. Yeah, you're not going to lose any of the reactants. That's the aim. So you can just keep heating.
Whilst the reaction is happening.
Whilst the reaction is happening, yeah, exactly. Okay? Because if you didn't have the condenser there, it will just vaporize off completely. Okay? So we will do that together. A bit of heating under reflux, but not with cyanide. Okay? Like I say, death is not one of my aims for chemistry students. Depending on how you do on your tests, obviously. Just checking you're listening. Okay, so reaction with ammonia next. I reckon you've probably picked up a pattern here as to what's going on. So we'll take out 1-bromobutane again and react it with NH3. This time, to make it happen, we don't reflux it, but we heat in a sealed container.
What's the difference between these two?
So, reflux is not sealed. This needs to be sealed because otherwise we can't condense the ammonia off.
So when someone put this in the one under reflux, would some of it escape?
Tiny amount, yeah. But not, yeah. It's much easier to do than heating it in a sealed container is actually quite difficult to do. Yeah, because the pressure increases and you might blow things up. Okay. Now, can anyone work out what's going to go on here? Tell you what, if we work out what our small product is, we can probably work out what the organic product is. The small product is HBr, exactly. Which leaves us a compound like this. C4H9NH2. Another new looking organic compound. We've not seen that group before, and we learn much more about this group in year 13. Okay, in our year 13 organic chemistry. All we really need to know now is what it's called. Okay, this is an amine. Some of you kind of probably come across words like that before, particularly if you're a biologist. What does that remind you of? Amino acids, exactly, okay? Amino acids have a group that is exactly this, NH2. Okay, they also have an acid group as well to make them amino acids. So this would be butyl amine. Wow. Oh my God, that's like huge amounts of information. Now maybe I'll just give you a few seconds to absorb and make sure that you've got your notes that you want on that. Okay. Let's move this along. Fantastic. Right. So we're going to go on to our mechanism now. I'll just make the molecule a bit shorter, but we'll still use the bromo version of a halogenoalkane. So I've got 2 carbons in the chain. So this is just bromoethane. Okay, I've just drawn out the H's on that, so I know what's going on around this bond here. Okay. Now, first of all, it's really important usually for any mechanism. I want to put in any like partial charges that we've got, particularly because of any electronegativity. So, is there a charge, like a delta charge, that I can put on to this somewhere? The ads? Okay, delta negative on the BR. So then what else should I put in? Delta positive on the carbon, exactly. Okay, so I want to put in my charges there. Which part of the molecule do you think is now kind of susceptible to being attacked? The carbon, yeah? It is, I mean, it's that bond, but in particular it's the carbon. It's delta positive, okay? Now, we've already talked about electrophiles, haven't we? What is an electrophile?
It's the one that accepts electrons and is attracted to areas with high electron density.
Okay, so it's going to accept electrons and it's attracted to areas of high electron density. That's a really good answer, thank you. What do you think the opposite of an electrophile is? A nucleophile. Okay. What were you going to say? Electrophobe. Okay, in a way, I guess. Yeah, it's maybe we just we don't like the hating in chemistry. Yeah, we like the loving. Okay. So rather than hating the electrons, it loves the nucleus instead. Okay, so we use the word nucleophile. Yeah. So a nucleophile is attracted to positive areas, okay? So what does that mean it's probably got a lot of if it's attracted to... Exactly, it's got a lot of electrons, Leah, thank you, okay? It's got electrons to give away, it's possibly got some kind of partial charge itself, okay? Or maybe just a whole negative charge. Most importantly, it's going to have a lone pair of electrons, all right? So, let's actually put this in. We're going to have a nucleophile is an electron pair donor. Essentially, that's a really short definition of what a nucleophile is. So, we're going to do, I'll work through this one with you, then I'll try and get you to do one. Okay. OH minus is a nucleophile. It's got a lone pair of electrons that it can donate on the oxygen. So I'm going to put them there. Alright. It's actually really quite straightforward, this mechanism, or at least it is at first. We can do it almost in one step. Alright, so OH minus. Now we've got to start with our curly arrows. Okay, we know where does a curly arrow have to start? Okay, it needs to start from either a bond or from a lone pair of electrons, yes? So in this case, where's it likely to start from? The lone pair of electrons on our OH. There we go. So I can do a nice curly arrow round here to where it wants to attack, onto the carbon. There we go. Love my curly arrows. When that happens, this bond, C to Br, can break. So we show the electrons moving from the bond to the Br. Do my arrow down because I don't want to get in the way of my definition of a nucleophile. So that leaves me with exactly what I started with, but the OH plus Br minus. There you go. That's actually really, wow, really simple. Yeah, that's all I need on there. So this mechanism, well, we use the nucleophile, so that makes it nucleophilic. Nucleophilic, one or two of you have just said it, nucleophilic substitution. Okay, we have substituted the bromine for an OH, so it's a substitution reaction. Okay, is that what you were about to ask? Yeah, why is it substitution? So we've removed the Br, but we've added in the OH, so we've substituted them. Okay. Some of you may well be asking yourself, maybe not, depends how well you were listening earlier. I said something when we were talking about the primary, secondary and tertiary halogenoalkanes. I said something about an ion. And there's no carbocation in this. Okay, you may have noticed that, you may not have done. But actually, secondary and tertiary halogenoalkanes will undergo a slightly different mechanism, slightly different version of nucleophilic substitution. Okay, that is right at the beginning of our year 13 organic chemistry rather than this. So for year 12 we only need to know this really simple nucleophilic substitution mechanism. Okay, now what I want you to do the same with NH3 as the nucleophile. So we need to be able to draw, recognize two different versions of this mechanism, one with OH minus and one with NH3. Okay, so your task for the next couple of minutes, without looking at it in the book, is to see if you can do the same thing with NH3 instead. Okay? Go! Okay, folks, let's have a look at this one. So to use NH3 instead, let's see what happens, okay, and see if you've actually come up with something similar to how I would do it. I've got exactly the same molecule, I've kept that exactly the same. We've got NH3. We need to show a lone pair. Where is the lone pair, by the way? Huh? On the N, on the nitrogen, okay? We'll pop it there. Yeah? Notice, by the way, it's got no negative charge with it. That's going to affect something afterwards, okay? But hopefully you've got the same attack towards this. Okay? I reckon everyone would have done that exactly the same way. You've got the same breaking of the bonds here. Okay. That's good. So we've broken the bonds. So what's our next step going to be? Let's have a look. We've got C, H, H, CH3 there. But then we've added on the NH3. We've removed Br minus. Okay, now I reckon you would have got this far and you may have started to get a little bit confused at this point. Yeah? Because something important over here you probably weren't able to work out, you weren't sure about. Okay, if this comes out, these two molecules together, have they actually got a charge, a full charge on them? No. But we've got rid of a Br minus. Okay? So what must this have on it? It must have a positive charge on it, okay? This NH3 group here is now positive. Alright? I don't know if anyone worked that bit out or not. Possibly not, okay? That means we need to have another step. Can I remember the other step? Probably not. I should. Yeah, actually that does show it quite right there. The positive should be with the N, okay? I just moved it a tiny bit. It was more or less on the N, but not quite. Okay? Why?
Yeah.
Why is it a positive charge? Because this already had a lone pair here.
Yeah.
Okay? If it was neutral, it would have a lone pair here. This hydrogen, therefore, has got kind of less electrons than it would normally have.
Right,
Yeah? So there is a positive charge there. It's a bit of a you'd have to go through the whole dot and cross diagram to really work it out, but there is a positive charge there. You're just going to have to take a little bit of my word for it. Okay? So the next step, there is another little step in here. It's important. Okay? We need another NH3. And this is the bit you probably didn't get. Okay? We need this to work and break a bond here. The electrons go in. Is that right? Yeah. Is that the right way to do it? Or is it from there to there? Oh! From the bond into there. So the bond between the hydrogen and the nitrogen can break, caused by another ammonia. That's the tough bit to remember. And that leaves us with C, NH2, 2 H's, CH3, plus NH4 plus. Okay, that is the ammonia working. Yes, that's much better. Working like a base. Okay, to pull away hydrogen ions. And that leaves us with our final product. Okay, so you probably have to do a little bit of a change to your notes, which is all good. That's where the learning comes from. Yeah.
Where does the BR go?
The BR is still there in solution. I just didn't put it onto my second step. That was all. Okay, it has been produced. It is there, but I don't need to add it onto my next step. Okay.
So this isn't this one.
It is that exactly the same as that. I will do it the same as that. Yeah. And it would react with the NH4 plus would react with any Br minus and make NH3 and HBr. Okay. I know it seems a bit odd. So that was a bit more difficult than just doing the OH minus. Anyone got any questions about that? Because I'm just going to kick this on straight away if not. You okay? Question, go.
For the NH3, NH3. So it's the one that causes the break between the N and the H bond. Is that what's happening?
Yes.
Okay, but then where does the chromium go exactly?
Aha, that was what Angelina was just asking as well. Okay, so the bromide ion that's still there, I haven't drawn the bromide ion in the third step because it's already been produced. You could look at it and you could say, well, the bromide ion would react with NH4 and most likely regenerate some NH3 and some HBr.
It's just added. Like,
Yeah.
okay, then.
Jemima.
NH4 was always made like in this reaction.
Yes. Yeah. It needs to be made in that mechanism. Yeah, definitely. Okay. And it's just important just to kind of break that NH3 plus group up, okay, and break it down to an amine, something without a charge. Yeah. Okay, so there's one more reaction with halogenoalkanes. This is a really, really short section. We've almost finished it for today. This one doesn't need any kind of mechanism with it. It's not a substitution reaction. Now, can I take the top bit off? Yeah, everyone's got what they need from it. There is an elimination reaction with halogenoalkanes. What do I mean by elimination, by the way? Removing something, exactly. If I want to eliminate James, and I always pick on James for those nasty things, don't I? Yeah? Then I want to remove him in some way, some nice, non-violent manner, clearly. Okay? So, elimination is removing something, and we can do elimination with halogenoalkanes. In fact, it uses the same reactants as we've already used, but we just changed the conditions a bit, okay? So when a halogenoalkane So, when we get a halogenoalkane and we heat it with ethanolic potassium hydroxide, what do you think I mean by ethanolic? I'm not sure we've come across that word before either. What does it kind of say to you?
When the solution contains ethanol and salt.
Okay, very good, Ahmed. Yes. So, rather than the potassium hydroxide being dissolved in water, it's dissolved in ethanol. So ethanolic is, rather than aqueous, which would be dissolved in water, ethanolic is dissolved in ethanol. So when we heat it with ethanolic KOH, we get an elimination reaction. So let's take that. I'll draw the whole thing. So it's KOH in ethanol. So if I'm going to eliminate things, I'm removing atoms. If I remove atoms from this, what kind of thing must I produce, do you think, if I'm going to remove atoms? I need to make a molecule of some form. It's not going to have a charge on it or anything like that, but I'm going to take away some atoms. A what?
An alkane.
An alkane? But I'm taking it away completely. I'm not putting anything else back in. It's just eliminating. So if I was to eliminate this bromine and a hydrogen, what would I have to have there? A double bond. Yeah? I need a double bond. Okay? So this will form, from a halogenoalkane, a alkene. Yeah? Where did the bond come from?
Yeah. Like where, like, they could have just all, randomly appeared. So, like, did it come from the ethanol?
Well, it comes because the ethanol, or not the ethanol, it comes from because the hydroxide ion can remove one of these hydrogen atoms.
Oh, and then the bond.
And then a bond can form.
Oh, okay.
Yeah, and it will also allow one of these to leave as well.
Yeah.
Yeah? So you're left there, when you eliminate everything, you're left with H2O and KBr. Okay? No mechanism needed for that, but you do need to know what will happen and the difference between having potassium hydroxide dissolved in water and potassium hydroxide dissolved in ethanol. Okay? And that's a really kind of popular little piece of knowledge to test. Okay? Wow, we haven't got much time left, so I've talked like for way too many minutes of this lesson. What I want you to do, just to see that you've got some understanding from today, in your book, page 203, I want you to have a little look at question number 1 and question number 2. Okay? They're quite short.